You see, like recording started.
Yeah. Say something.
Okay. Hi. This is our oral lab report.
Wait.
For CHEM 108.
Okay. What?
Which one?
Do you think it's like? Okay. Hopefully it's working. Okay, go.
Hi. This is our oral lab report for CHEM 108. And we did it on the determination of an equilibrium constant. Absorption spectroscopy, a fundamental technique in analytical chemistry, investigates how substances interact with light of varying frequencies. When photons of different frequencies pass through a substance, they are either absorbed or transmitted, providing valuable information about the substance's composition and concentration. In our experiment, absorption spectroscopy serves as a vital tool for quantifying the absorbance of an indicator at specific wavelengths, enabling us to determine its concentration in solution. Equilibrium constants, another cornerstone of chemical analysis, elucidate the balance between products and reactants in a chemical reaction at equilibrium. Understanding these constants help us predict the extent of a reaction and assess its equilibrium position. Specifically, in our experiment, the equilibrium constant Kx characterizes the dissociation of the indicator into its acidic and basic forms. Finally, pH indicators of classic acids play a pivotal role in monitoring the acidity of solutions. These indicators undergo distinct color changes in response to fluctuations with hydrogen ion concentration, allowing us to visually assess pH levels. By comprehensively integrating absorption spectroscopy, equilibrium constants, and pH indicators, our experiment aims to unravel the intricate relationship between these concepts, offering valuable insights into chemical equilibrium and solution behavior. So the equation Cx equals the concentration of H times X plus X minus states that the total concentration of the indicator in solution is equal to the sum of the concentrations of its acidic and basic forms. It reflects the principle of mass conservation in chemical equilibrium, where the total amount of a substance remains constant regardless of its chemical form. In the context of pH indicators, maintaining a constant total concentration allows for consistent color changes and reliable pH measurements. For the equation, A equals epsilon times B times C. A represents the absorbance of the solution, epsilon is the molar absorptivity, B is the path length of the light through the sample, and C is the concentration of the absorbing substances in the solution. This is Beer's law, and it states that the absorbance of a solution is directly proportional to the concentration of the absorbing substance, the path length of the light through the sample, and the molar absorptivity of the substance. This equation is foundational in spectrophotometry, allowing scientists to quantitatively measure the concentration of a substance in solution based on its absorbance of light. For the last equation, A represents the absorbance of the solution at a specific wavelength, AH represents the absorbance of the solution at a high pH, and AL represents the absorbance of the solution at a lower pH. This equation is derived from Beer's law and the equilibrium between the acid and base forms of the indicator. It establishes a logarithmic relationship between absorbance, pH, and the acid dissociation constant of the indicator. By plotting absorbance ratio versus pH and fitting the data to a linear equation, the value of pKx can be determined from the slope of the line. The purpose of this experiment is to determine the pKa of the indicator by measuring the absorbance spectra of solutions containing the indicator at varying pH levels. By conducting a series of measurements across a range of pH values, we can figure out how the equilibrium between the acid and base forms of the indicator responds to changes in solution acidity. Through the analysis of absorption spectra, we can quantify the concentration of each form of the indicator at different pH levels, allowing us to construct a comprehensive understanding of indicators behavior in solution. Ultimately, determining the pKa of the indicator provides crucial insights into its acid-base properties, facilitating its application in various analytical and experimental contexts. So for the equipment for this experiment, we use a 5 milliliter volumetric pipette, 150 ml beakers, 7 test tubes, 400 ml beaker, 10 ml volumetric flasks, a wet tank spectrometer, a pH probe, 7 cuvettes, a bowl, and 4 dropper bottles. We also used a 1 molar and 6 molar hydrochloric acid, a bromothymol blue for the indicator, and a 1 molar and 6 molar sodium hydroxide. For the procedure, we first calibrated the pH probe in the Data Studio program by immersing it in 2 different buffer solutions of pH 4 and 10. We then prepared buffer solutions using a 7 pH stock solution, 1 molar hydrochloric acid, and 1 molar sodium hydroxide to create 5 solutions of varying pH values from 6.7 to 7.0, 7.3, 7.6, and 7.9. Also, we prepared 2 high and low pH solutions by using the 4 and 10 stock solutions and 6 molar hydrochloric acid and sodium hydroxide. We then prepared indicator solutions by adding a buffer solution and 2 milliliters of indicator solution into a 5 milliliter volumetric flask for all 6 solutions. We then obtained absorption spectra for all solutions and saved data as a CSV file.
Now for our results. So if you look to the top left corner, that's the absorbance spectra of our pH solutions. And as you can see, there's an isobestic point at around 490 nanometers. And then we use this absorption spectra data to make the table in the bottom of 3 different wavelengths and their absorbance values for all pH solutions. We also made sure to note the absorbance values of the low pH and high pH solutions at these wavelengths because we would need them to compute the absorbance or the pKx's of the 3 solutions. We also, as you can see, the bottom table, that is the calculation of the log of the absorbance value at that wavelength minus the absorbance value of the high pH solution over the absorbance value of the low pH solution minus the absorbance at that wavelength. By using this chart and data, we were able to make the top right graph, which is, again, that equation as a function of pH at 425.6 nanometers. We also did this for the other 2 wavelengths of 565.9 nanometers and 622.6 nanometers. By graphing these equations onto this chart, we can see that the slope-intercept form results in an equation of 1.1x plus 7.88. The b in this equation is our pKx at that wavelength. And so by using these equations for 3 different graphs, we were able to find the pKx at 3 different wavelengths, which you can see in the bottom right table. And to find the final pKx, we did the average of these 3 values and resulted in a final pKx of 7.07. This gave us an equilibrium constant of around 8.51 times 10 to the negative 8 of bromothymol blue because we have to take the negative log of the pKx. So some things that we had to note and conclude were that the graph of the 425.6 nanometer was more reliable than the graph of the 622.6 nanometers because the R squared value for the first graph was closer to 1. It was around exactly 1, while the R squared value for the 622.6 nanometer graph was around 0.9. And so this shows that the relationship between the 2 variables was more linear in the 425.6 nanometer graph, and that makes it more reliable. We also had to note that if the volumetric flasks were filled too low, then the absorbance value would be too high for those solutions and we would get skewed results. On the opposite hand, if we filled the volumetric flasks too high, then the absorbance value would be too low due to dilution of the solution. And this opens up our experiment to error because it's very imperative that we get that we fill the volumetric flasks right up to the mark exactly and make sure that the meniscus is lined up, or the bottom of the meniscus is lined up with the 5 milliliter mark. The acidic and basic solutions had a max wavelength of 423.8 nanometers and 613.7 nanometers, which if we look at a color wheel is the colors violet and orange. we can use this to kind of, or by using this data, we can see that the color theory is proven because these solutions displayed an orange, yellow, and a deep blue color respectively. And if you look at a color wheel, 423.8 nanometers is violet, which is opposite of orange and yellow. And deep blue is opposite of orange. So it makes sense that they would display these colors and absorb wavelength of the of 423.8 and 613.7. We concluded that bromothymol blue is a good indicator for a titration of a strong acid and a strong base because the color changes at a pH of 7, which means that the solution is neutral because it's a strong acid and a strong base reaction. And we can see this because the pKa of bromothymol blue is around 7.07. Or that's what we got, and the expected value is around 7.2.
Thank you.
That's good.